Hey,
Hey, loud and clear. We're on the record, so feel free to dive right into whatever you'd like to discuss.
how do we analyze hydrogen atom if there is a Hilbert space given?
When we analyze the hydrogen atom in the language of Hilbert spaces, we're essentially talking about the state space of the electron's wave function. Each state, like energy levels, is a vector in that space. The Hamiltonian operator acts on these vectors and gives us the energy eigenstates. You'll see that the hydrogen atom states are just solutions to the Schrödinger equation, which form a complete basis in that Hilbert space. In short, we study how operators act on these states and how the probability amplitudes evolve.
So you mentioned about lot of technical term uh, like first the electron wave function, then the energy level in that vector Hamiltonian operator that gives energy eigenstate and the Schrödinger equations complete basis which forms. So, and the probability amplitude that evolved. So, I was thinking that given the hydrogen atom, how we can think that it is a part of Hilbert space.
Think of the hydrogen atom's electron as having a home in an abstract space. This home is the Hilbert space. Each possible quantum state of the electron, like the ground state or an excited state, is a vector in that space. The Hamiltonian operator, which encodes the system's energy, acts like a rule that tells you the energy each state vector corresponds to. So by placing the hydrogen atom in a Hilbert space, we mean its entire quantum description lives as vectors states in that mathematical space.
Why? Okay, I understand that postulates of quantum physics are directly applied to the hydrogen atom itself that will satisfy the axioms and given the Hilbert space. That is what I mentioned some of the point that you mentioned about like state, measurement, probability, energy levels, eigenvalue, that what you have mentioned.
Exactly. All those concepts, states, measurements, probabilities, fit neatly into the framework of a Hilbert space. It's basically the mathematical backbone that lets us describe everything we measure and predict about the hydrogen atom. So when we solve Schrödinger's equation for the hydrogen atom, we're finding the vectors in that space that match its energy levels and observable behaviors.
So why we talked about energy levels in the hydrogen atom state? Why not another thing? Because it has only two systems. Either it will.
We focus on energy levels because in quantum mechanics, these are stable, measurable outcomes, what we call eigenvalues. They're not arbitrary, they define the structure of the atom. Of course, we could talk about other observables like angular momentum or spin. It's just that energy levels are central to understanding the atom structure, how it absorbs or emits light, for instance. So they're our natural starting point.
How do we observe spin in of the hydrogen atom inside the Hilbert space? So I am wrong because saying the hydrogen atom spin is not sufficient. I have to precisely define subatomic.
You're absolutely right. When we talk about spin, we really mean the electron spin in the hydrogen atom. In the Hilbert space, the electron state is described by both its spatial wave function and its spin state. Spin is represented as a two-dimensional subspace, often described by up or down states. Observing spin means measuring with a spin operator, like the Pauli matrices, and you'll get either spin up or spin down with certain probabilities. So spin is just another observable in the Hilbert space, one that's key to quantum behavior.
What about because there are two things, hydrogen atom has one electron, one proton. So what about proton spin?
Ah, exactly. The proton also has spin, typically spin one half. In principle, the full hydrogen atom's Hilbert space would include both the electrons and proton spin states. However, because the proton is so much heavier, its spin doesn't typically affect the energy levels we focus on. But if we do a hyperfine analysis, like in the famous 21 centimeter line, both spins matter. In short, the full Hilbert space can represent both spins, and you measure them similarly, just accounting for both particles.
Okay, the term you mentioned about 21 centimeter line, uh, what was that? Hyperfine analysis.
Sure. The hyperfine structure is a tiny energy shift caused by the interaction between the electron spin and the proton spin. In hydrogen, this gives rise to a very slight splitting of energy levels. When the electron flips its spin relative to the proton spin, it releases a photon with a wavelength of about 21 centimeters. This transition is super famous in astronomy. It's how we study neutral hydrogen in space. So that's hyperfine structure, a subtle spin-spin effect.
Okay, this is pretty much clear. And what about the hydrogen atom that evolves in Hilbert space that we talked about in this case?
When we say the hydrogen atom evolves in Hilbert space, we mean the electron's quantum state changes over time. This evolution is governed by the Schrödinger equation. The state is a vector in Hilbert space, and the Hamiltonian, which encodes the system's energy, dictates how that vector changes. Over time, the state might oscillate between different energy levels or remain stationary in a stable state. It's this continuous evolution in the space of possible states that allows us to predict how the atom behaves and what we'll observe when we measure it.
So, what about basis state, meaning that hydrogen atom related and the Hilbert space?
In the Hilbert space, the basis states are like a set of fundamental building blocks. For the hydrogen atom, these basis states are the energy eigenstates. Think of the familiar N, L, M quantum numbers. Each state corresponds to a particular energy level and orbital configuration. They form a complete basis, meaning any possible state of the hydrogen atom, whether stationary or evolving, can be expressed as a combination of these basis states. In short, the basis gives us the coordinates to describe any quantum state of the atom.
So basically, the quantum number of the hydrogen atom we have to know earlier, or in the formulating the first time the hydrogen atom in the Hilbert space, so they know they have the quantum number and how that quantum number can be expressed in the Hilbert space. That is what the basis state meaning.
Exactly. The quantum numbers, like the principal quantum number n, the angular momentum L, and the magnetic quantum number m, are what label these basis states. They tell us exactly which energy level and orbital shape we're dealing with. So when we set up the Hilbert space for the hydrogen atom, we know that each basis state corresponds to a unique set of these quantum numbers. In other words, the quantum numbers are the coordinates we use to express states in this abstract space.
No, no. Did you understand that I was so for the first time how these basis states were introduced? Because in mathematics, this Hilbert space already have the definition to define the basis state.
Ah, I get you now. In the abstract, Hilbert spaces can have any basis suited to a problem. For the hydrogen atom, the basis wasn't chosen arbitrarily. Physicists solved the Schrödinger equation for the hydrogen atom. The solutions, those neat energy levels and shapes, naturally emerged. So the basis states are the actual physical solutions, eigenstates, that match the atom structure. In other words, the math was guided by the physics, and that's how we got this particular basis.
Oh, that was really intriguing fact. What about this Schrödinger equation that we talked about and how we understand Schrödinger equation in Hilbert space?
In the Hilbert space, the Schrödinger equation acts like a rule for how states evolve. It tells us how the state vector, representing the system, changes with time. The Hamiltonian operator, which is tied to the system's energy, acts on the state vector. Solving the equation gives you how the state changes, or for stationary states, what the allowed energy levels are. So in this space, the Schrödinger equation is the fundamental tool that connects the abstract math to physical predictions.
Okay, tell me So you are mentioning about, okay, this Hamiltonian operator, energy levels, and all those things. Okay, that this Schrödinger equation basically connects all those things and give the solution to the system. But we have the two-level system, and there Hamiltonian is defined, and then solving those, this Schrödinger equation help us to understand and give the appropriate. So tell me the uh, very intuitive fact about this hydrogen atom in the Hilbert space.
The intuitive essence is this: the hydrogen atom, though a physical object, is mathematically like a point in a vast abstract space. Each possible state of the electron, its energy, orbital shape, and spin is a vector in this space. The Hamiltonian and Schrödinger equation act like the rules of movement, telling us how that vector changes or which vectors are special. The energy states. In short, Hilbert space gives us a neat mathematical stage to fully describe and predict the hydrogen atom's quantum nature.
Okay, thank you.